Welcome to Pre-Calculus and our first flipped classroom video of the year. This topic will cover functions. Some of this you will have seen before, but you might need a little bit of review, and some of it might be a little bit new. By the end of this section, you should know the definitions of our important vocabulary. It says see below, but you'll have that sheet in class. Function notation and interval notation. You should understand the importance of function notation and how functions relate to relations. And most importantly, at the end of the section, what should you be able to do? What skills are you going to be asked to demonstrate? The first objective, the first skill is determine if a relation is a function. You have to do that several ways. Objective B, you need to be able to evaluate a function at numeric values. You need to determine the domain of functions, and you need to be able to solve applied problems. This first video will only address objective A. If I pull that up here, we're only going to address determining if a relation is a function within this video. There will be follow-ups to cover the other objectives. All right, so here we go. Some initial terminology, which you may or may not have seen before. We'll go through it at a moderate pace. A relation, a mathematical relation, is any correspondence between two sets. And we will illustrate that in a moment. But one example is that you have a name and a phone number at which you can be contacted at. And those two things, those two values, those two items, their two sets are linked. Your name is linked to a phone number that you can be contacted at. Any sort of connection between two sets is what a relation is. The domain is the first set, or what we call the input of a relation or correspondence. The range is the second set, or the output of a relation or correspondence. Pre-calculus in general spends a lot of time talking about domains and ranges, so it's very important that you can identify and be comfortable with those two words. And those will be addressed later on in this section as well. Probably most important of the vocabulary words, this initial terminology, is a function. Because one way to think about pre-calculus is a study of functions. A function is a special case of a relation where each element, that's each item, of the domain corresponds to exactly one element in the range. If I take my phone number example from a moment ago, there might be multiple phone numbers at which you can be reached. Maybe we can reach you on your cell phone, and maybe your house still has a landline. That would be a relation, but not a function. Because your name, the domain element, can be matched up with or corresponds to two phone numbers. And we want the scenario where each element is paired to exactly one element of the range. And that's really the important part of this, exactly one element. One phrase I use, and you'll hear me use it in class, is that if we know the input, we know the output. There's no multiple choices. It's here's one input, here's one output, and we can move on from there. Let's take a look at a couple of illustrations. Here we have a correspondence between a person's name and their blood type. And we took a moment here and we put them together as ordered pairs. And it's always, since there's a correspondence, there is a relation. So it's yes, this is a relation. We can pair it up. But I guess the question becomes the important question. Is this a function? Is each input element, each domain element, paired with one element in the range, the blood type? Well, Michael pairs up to type A, Tanya pairs up to type A, Dylan types up to AB, Trevor matches up with O, and Megan matches up with O. And each person only has one blood type, and it would be unusual to have multiple blood types. I'm not even sure that's possible. So in this particular case, each item within the domain, the person, pairs up with exactly one blood type. So the answer, is this a function? Yes, this is a function. Another illustration, time of day and what competition might be taking place. Maybe it's a high school, and they got a lot of things going on, they got a schedule of fields. If we call this our domain, the time of day being our starting points, our inputs, and our competition is our range, at 1 o'clock we have football, 2 o'clock we have volleyball, 7 o'clock we have soccer, 7 o'clock we also have basketball. So it's almost like instead of breaking these, I don't need this 7 o'clock, and I could draw this. So while there is a relation, yes, relation, there's a correspondence that each item in the domain is paired up with something in the range. But is each item in the domain paired up with exactly one element of the range? And the answer is no. We take a look at 7 p.m. At 7 p.m., there are two competitions going on. So the answer is no, not a function. So almost everything is a relation. Relations are very broad, very vague, can be used in a whole bunch of places. But those functions are specific cases. All right? So let's look at some other places here. Here's an example for that objective. Determine if the relation is a function. One very quick way to do this is to create a mapping diagram. Where you list your domain elements, you list your range elements. So my domain elements are -3, 2, 3, and 6. My range elements are 4, and I've got 4 again, so I don't need to list it. 5, and 4 again, so I don't need to list it. And as we see, -3 paired up with 4, 2 paired up with 4, 3 paired up with 5, and 6 paired up with 4. And we look at this and we say, does each element of the domain pair up with exactly one element of the range? And despite all those arrows pointing to 4, the answer is yes. This is a function. -3 pairs up to 4. -3 only pairs up and corresponds to one element, 4. 2 pairs up with 4. It only pairs up with 4. 6 also pairs up with 4, but 6 only pairs up to 4. So while they all pair up to 4, they each only pair up with one output. And so on and so forth. So there's an example of that. If you would like to take a moment, pause the video, make a mapping diagram, try that example on your own, just for a little bit of practice. Functions, before, these functions that we had were defined explicitly by ordered pairs. We can also have functions defined by equations. Now the question would be, once again, is this a, let's change colors. Is this a function. How do we tell? Does each element of the domain, our x's, pair up with each element of the range, our y's? We can do some calculations. If I choose, let's say, a 3 here, that means y equals 3 squared minus 3 times 3. So that's 9 minus 9, which is 0. I could have negative 2. Y equals negative 2 squared minus 3 times negative 2. So that's 4 plus 6, which is 10. And I don't know, maybe I'll choose 0. 0 is a nice number to work with. Y equals 0 squared minus 3 times 0, which gives us 0 minus 0, which is 0. So I have a very short list of inputs, 3, negative 2, and 0. And I can see that 3 matches up to 0, pairs up with 0. It's paired up, corresponds, but it only corresponds to 0. So far, so good. 3 only corresponds to 0. Negative 2 corresponds to 10. I put in negative 2, I got out a 10. 10 is the only thing I got out. Negative 2 corresponds to exactly one output. So far, so good. And then 0 corresponds to 0. And that's okay, even though the 0 in the range is being repeated, because the 0 in the domain is paired up with only one element in the range. So far, so good. The problem with this technique is I have only chosen 3 of the infinite possible inputs. And I don't have time to check all of them. So the question becomes, how do I know if it works all the time? I can't possibly test every input value. There's too many of them. So how do I test all of them? One way to determine if the equation is a function of x is to work with it algebraically. And here's how we do it. Determining if an equation is a function of x. So this is still objective A. It's just a different technique. One way we already looked at it was if you have ordered pairs, you can use a mapping diagram. But if you have an equation, it requires a different technique because your mapping diagram would be infinitely large. So our basic technique for determining if an equation is a function of x is to solve the equation for y, and hopefully you know what that means. That's our first step. And then after that, look for indicators of multiple values. And I'll put a note on here. Usually, that means you're going to have a plus minus within your solving process. That's kind of the biggest one of them all. That'll take care of like 95% of any possibilities. So if you solve for y and you end up with a plus minus, the general idea is that it's probably not, or it is not, going to be a function. So solve the equation for y. If you don't remember what that means you got to rewrite the equation so that you isolate the y by itself in the equation. And we'll show an example of that right now. So example 2, demonstrate that the equation does not represent a function of x. So I'm giving you a little bit of hint here that I'm already telling you that these are not going to be functions. If I look at the first equation, I could ignore the second one for a moment. X equals y squared. So while y is alone by itself, we haven't solved for y. This is solved for y squared. So how do I turn the y squared into a y? Well, general solving techniques, I'm going to take the square root of both sides. And when you take the square root of both sides, you end up with a plus or minus. So it's plus or minus x. Plus or minus the square root of x equals y. When I see this, and I see this plus or minus right here, that says to me, hey, that is not going to be a function. And if I illustrate that with some specific values, if I choose x equals 16, and I have my equation y equals plus or minus the square root of 16, that means y equals plus or minus 4. Let me make that plus or minus a little bit better. Then if I use the mapping diagram I had before, domain, range, I had a domain element of 16, and I got two range elements of 4 and negative 4. So if I had an input of 16, I get an output of 4, and I get an output of negative 4. So I violated the definition, which says each domain element is paired with one range element. Here, my one domain element is 16, but it's being paired with two range elements, 4 and negative 4. And so once again, the big indicator was going to be that plus or minus. So I knew that this was not going to be a function. Now, on the other hand, when we have absolute values, and your absolute values might be a little bit rusty, but the absolute value also gives us a plus or minus. If I was going to take this equation and solve for y, it becomes y equals plus or minus x as well. So, I mean, a particular pairing that would work here, my domain elements are my x's, my range elements are my y. If I chose x equals 5, I could use 5 or negative 5 for y and have a true statement. If I take my original equation, I can demonstrate that. It means I can write 5 equals the absolute value of 5. But I can also write 5 equals the absolute value of negative 5. So I have my x being 5, and I've got my y being both 5 and negative 5. I don't know how that green is going to highlight over green. But once again, one domain element being paired with two range elements. The big indicator was that when I solved the equation for y, I got that plus minus. And that's going to be the big indicator that we're going to use. All right. Here's a practice for you. If you want to pause the video, try it yourself, see what happens, and then come back in a moment. Okay, maybe you're back. Hopefully you tried it. I want to take this equation, solve for y. I'm going to subtract x squared from both sides. Y squared equals 1 minus x squared. Take the square root of both sides, but once again, when I take the square root of both sides, I'm going to have a plus or minus. As soon as I see that plus minus, oops, that's not a good color there. Hang on, let's change that. As soon as I see that plus minus right there, I can say that this is not a function, not a function of x. So that's a plus minus. So far, we've covered two things. We have covered determining if a relation is a function from pairs, determining if an equation is a function, and last thing is to determine if the graph is a function. And just about everybody's seen this before, and this is where we use the vertical line test. Vertical line test. And the vertical line test says, if a vertical line can intersect a graph at more than one point, then the graph is not of a function. And this vertical line test, it checks each input paired with exactly one output. So get that written down. You might need to pause it to write it down, or maybe you're just watching this, but I'm going to go on to some illustrations here. So I've got a couple of examples here. One is the squaring function. if I take a vertical line, let me find a vertical line on here. If I draw some vertical line, make that nice and vertical, and I drag that vertical line across, oh, I want to do that. If I drag the vertical line across, I'm missing a little bit here. My orientation is a little bit off. If I drag that vertical line across, I can see that I'm not intersecting anywhere. I'm intersecting at 1 point, 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 1 point. Good. I only intersected it at 1 point, at maximum 1 point. So since my vertical line only intersected the graph at 1 point at a time, this is the graph of a function. Good. Now I have a second example down below. Let me scroll a little bit here. And the question is this graph going to be a function as well? So if I take my vertical line, start here, scroll it across, no intersections, no intersections, no intersections, that's all good. I get to here, one intersection, that's okay, that's no problem. But as soon as I get over here, now I've got two intersections. So I can say, since my vertical line intersects the graph at more than 1 point, it is not a function. And we could just stop there, but pre-calculus asks the question, why, a lot. So let's take a look at those 2 points of intersection. Those 2 points of intersection are going to have the same x coordinate, but different y coordinates. So if I looked at it as a mapping diagram, domain and range, I have one x being paired up with two different y's. And so there's my justification for why the vertical line test works. If I intersect the graph at 2 points, those 2 points have the same x coordinate, the same domain element, but two different outputs, violating the definition we started with about 20 minutes ago, 1 to 1. All right, I hope you found this helpful. We'll keep working through it in class, but this was just to get you going a little bit on the topic that we're going to look at. Thank you.